The M file starts with reading the two images, and they are converted into gray because the program works on gray images only. Now we'll use the function detect shift feature to detect the shift features, scale invariant feature transform. This is the mean of shift. This is the short of the shift. We'll detect these shift features for each pixel and save them in points in image 1 and image 2. Then we'll extract these features from image 1 and image 2, and we will put this in feature 1, feature 2, extracting these features. The third function, match features, will find the matched features between the two images, between these features. And we'll give you an index for image 1 and index image 2 to have the matched points in image 1 and image 2. We'll see these match features in this function, plot function, to see the match points between image 2 and image 1. The H matrix, homography matrix. Now, how to find the homography matrix is very important. We will define it first as a projective 2D of I3, identity matrix I3, and we will use this as the projective 2D will make it an object variable, which consists of the I matrix, the identity matrix, and a property called dimensionality. All of these are an object for the H matrix. Now, we defined MATLAB, a user-defined function called called homography, so as to find the H matrix and also the inlier points. This function will work on the matched points of image 1 and matched points of image 2. After we find the inliers, we will draw the inliers on the two images to compare with the first image of the matched points and just to see where are the inliers out of them. The last step here, we work the two images using the H matrix for image 1 and image 2, H matrix of 1 for 1, and this H matrix help warping the two images together. We will use the IM fuse to fuse the two images in one image and try to find the whole image of the two images. Now this is the function defined for the homography matrix, works on matched points of the two images, give the H matrix and the inlier points. This for loop for high number of repetition. F is matched one location. If the location of match points in 1, this is the match points in 1, take the location because they are all objects. We take the location part and store that in F. Also from matched points in image 2, R. F and R, we will use them we'll work on them to find the H matrix. Here we take 4 random samples of F and R, and these samples will use them to find the homography matrix using these 4 samples. This homography matrix is stored in A, and this in A matrix will be the input for the MATLAB defined function singular value decomposition SVD. This will find the H matrix for us. By finding V, this V, the last column of it is H, and H will be reshaped to 3 by 3 after being a vector to give us the H matrix. Now the H matrix, you will use it to find the inliers. We will give du and dv, which is the width of the two dimensions that will determine the inliers, and the inliers are that points that are within that width, which we used as a 40 width of that strip. Now these inliers are used after that. we will find the H matrix again of these inlayers. The inlayer points are then taken, inlayer points, one point by point, or let's say 2 points of match of point by point from every image. We'll find the H matrix and save that in a matrix A. All of these H matrices will be saved in the A matrix, which has the size of 2n, which n is the number of n layers. This huge matrix A will be also, again, the input of the singular value decomposition function in MATLAB to give us V, which gives us the H matrix again. This H matrix is the final H matrix that we have and will be used, as said before, to make the warping of the two images. And this is the H matrix.